Today we're going to talk about an algorithm, actually a sorting algorithm that is most commonly used by people when they're writing things, mostly because it's pretty efficient in practice. And that's a method you've probably already read about called Quicksort. So Quicksort, like merge sort, works using divide and conquer. So this method is actually a little bit more similar to binary search than merge sort is. They're both work in a very similar way where you're taking everything and splitting it into two and solving those independently. So the basic idea for Quicksort is that you choose a middle value. So this middle value doesn't necessarily need to be the middle in the entire range of values. You don't need to necessarily even find the middle value in the sorted list. We're picking one sort of at random, and we're going to assume that it's the middle. And then what we do is we rearrange the elements so that the left side contains all the elements that are less than or equal to that middle value, and the right side contains the ones that are of a higher value. And then we recursively run Quicksort on both the left and right halves of the array. So sort of pictorially, say we have this array here, right? So this is some array of numbers. We don't know the values. This is just a little toy example. And we're going to pick a middle at random. Notice that the middle is neither located in the middle, nor do we know that it's in the middle of the values. We're choosing it, at random, pretty much. And now that we have that middle value, we can decide all the other values, whether they are bigger or smaller. So let's say that the smaller values are going to be green, the bigger values are going to be red, right? So we can label each one of them as bigger or smaller. Then what we want to do is, like we said, rearrange the elements so that the left side contains all the elements less than or equal to the middle, right? So we're going to take all the things that are less than and move them to the left. All the things that are greater than, move them to the right. And now we have an array that's not necessarily sorted, but we at least know that all of the things on the left half are smaller, all of the things on the right half are bigger. So that should sound somewhat familiar, right? When we're doing binary search, because the list is sorted, we know if it's smaller, it has to be on the left. If it's bigger, it has to be on the right. Except now we're using that idea for sorting, right? We're putting all the things that are smaller on the left, all the things that are bigger on the right. And now we can recursively call Quicksort on the left and right halves. So now we have some new input. So it's this thing here in black, right? We're going to ignore the part in gray for now. And again, we're going to find a middle. We can assign what side things are on and move them around. So let's go through a quick example of Quicksort. Right? So this is the same set of numbers that we had seen in all the other sorting examples, right? And we're going to randomly choose a middle value. I'm going to say 2, right? I'm going to randomly pick this 2. And we can color everything, whether it goes on the left or the right of the 2, right? And really all we need to do in order to get it so that the left contains the things that are less than or equal to, and the right contains the things that are greater than or equal to, is to swap these two values, right? And now all of these things are less than or equal to 2. All of these things are greater than or equal to 2. Notice that the middle value doesn't necessarily end up in the middle, right? It doesn't have to. We're using its value to partition the set into 2. Okay? Then we're going to make a recursive call here, right? So just on this subset, we're picking 0 as our middle. And we're going to move things around. Really, we're going to swap. We're going to, this guy's going to go there. That guy's going to go there. We're going to move those to there, right? The way they do it in the book is they go along and they have 2 pointers. They start here and here. And they move this in as long as it's smaller. And they say, okay, well, I've gotten here and here, and these are both on the wrong side. So I'm going to swap those two. Right. And So now we're here and here. And again, they're in the wrong order. So we're going to swap those two. Right? And that gives us this guy. And again, we're going to partition here. When we do that, we end up with this array, and say we pick negative 20 as our middle. Clearly it's not the middle, right? But that puts negative 20 on its own and negative 3 and 0 on their own. Right? Negative 20, we know how do you sort a single element? Well, it's already sorted, so we don't have to do anything. So then we go back up, and it doesn't really matter which of these we pick as the smaller one. Well, it does, but we might end up in an infinite loop if we don't pick well. But say we pick negative 3 as our smaller one, then it gets separated off, and so does 0, and we end up back here. Right? So now we've finished sorting this whole part, and we're back to these guys. Well, these have the same value across the entire range that we're looking at, so we can stop. And it goes back up, and now we're looking at the second half. Right? Now we're back at our original call. We've already sorted this left half, and now we need to sort the right half. So here we're going to pick a middle. We picked it to be 27. So 22 and 27 end up on the left. 81, 71 end up on the right. We take these guys. They're already sorted, but we would split them in half. Here we're splitting in half. 71 was our middle, so it's going to go on the left. 81 is going to be on the right. We end up swapping them. So if you follow out the entire tree, right, these are all of the operations that we did. We had this original array. We split everything up one side and then the other. This is actually after we've already done that operation, right? And we take this half and run a separate problem, this half and this half, and we keep breaking it into smaller and smaller pieces, right? So if we were to break it exactly in half every time, this is a question I've asked multiple times, but if we were to split it exactly in half, what's the height? Well, if we keep splitting it exactly in half, we know the height is log n. Right? And if we look here, all of that movement, how many swaps could we possibly have to do? Right? We could end up doing n over 2 swaps. Right? So order n swaps. So I think you know where I'm going with this, right? We're going to ask about the running time. Well, the best running time is exactly if we split it in half. We might have to do n swaps, which means our best case running time is n log n, right? N squared depth in our tree, n swaps along the length. But here's the question I have for you. What's the worst case running time? Well, what if instead of, in this first round, instead of picking 2, I had picked 81? Well, 81 would have left us in a... What if I had picked negative 20? Well, negative 20 would have moved here. It would have pushed everything else over here, and we would have run the next iteration with everything except negative 20. And then if by chance I had picked negative 3, then it would be negative 20, negative 3, and then we would have run on the entire set. So in that case, how deep is that tree? Well, in that case, the tree depth is n. So if the tree depth is n, if we're doing order n work at every level, then the worst case running time is n squared. So in practice, this is why we randomize what we choose as the middle, or we choose the exact middle. Sometimes you'll see both. But in expectation, right? So on average, it's going to be n log n. Right? So it's very fast on average, and in its best case, but its worst case is n squared.